All right, I'm on. Can you hear me?
Yes.
Awesome. Hola. Gracias para invitarme. Again, that's the extent of my Spanish. I'm practicing it, but it's not that great. I understand most of what you're saying, but I can't respond. My talk is about HPC. How many of you know what that means? Wow, not a lot. Cool. HPC is interpreted typically one of two ways: highly parallel environment or highly performing environment. You don't always need parallelization. It's not always possible, but typically you want this environment to be as performant as possible. And HPC traditionally is known as supercomputers. This is not exactly what I'm talking about. If you're interested to learn more about supercomputers, Google top 500. There are really some big ones out there. China is leading right now. And there are 500 plus supercomputers out there. So it's a pretty exciting field. This is a smaller chunk of that. First, a little bit about me to explain where I'm coming from. I am currently employed as the director of HPC at Pomona College since December 2017. I've been building HPC-type environments since 2007, starting at 454 Life Sciences, a company in Brantford, Connecticut that was acquired by a big pharma company called Roche. I'm in IT since 1995. Yes, it doesn't look like it, but it's true. Just to give you an idea of what I was working with back then was coaxial networks, B-tree databases, and DOS/6. That was a long time ago. I was a consultant for 2 years and with an invaluable experience focusing on cloud and data management and doing assessments for 50 plus companies, government, academia, commercial, pharma. I built a couple of infrastructures for life sciences companies from scratch and revamped a couple of others. I was a bioinformatics analyst, which meant talking to scientists and programming. Background back then was Java, Perl, CGI, HTML, CSS, and recently I'm working with a lot of Python and Go. Scalability and usability are two important factors for those two. And then data science involves Rust, Scala, and Haskell a lot. And I'm really a systems engineer. I do not specialize in any particular field. I like to know how everything works together. Where is Pomona College? It's in Claremont, California. It's a part of Claremont Consortium. There are 5 undergraduate schools and 7 graduate schools. It was a #1 on Forbes list of liberal arts colleges in 2017. That's a lot of responsibility for me. And it's kind of in the shadow of other big, well-known schools like Cal Poly, UC Irvine, UCLA, and UCSD. And these are just nearby. I'm not even talking about the East Coast. So I'm not going to go in detail over other schools, but if you want to learn a little bit more about what kind of other schools are near us, you can look at the slides later. And it's a beautiful campus. So I have about 25 slides, and I'm going to kind of go slow. I apologize in advance for rushing. You can talk to me afterwards if you have questions. So I made a plan of action when I started this job. In December, I started interviewing faculty and staff and research what other colleges have done, specifically liberal arts colleges. Then I shopped for hardware, chose a vendor. Then I ordered, and now I'm waiting. So as soon as the hardware shows up, I'm going to build it with the goal of having it ready for the summer research programs when I'm going to have students available to help, and I'm going to train them to support the environment. Teaching is going to be integrated throughout 2018, and then I'm planning to scale it over the course of the next year and eventually build a local and distributed Exceed-like grid by 2020. The goal is to offer a blueprint to other institutions. I am focusing on research and teaching, but I suspect this might be applicable for smaller organizations. I'm going to skip this for now. If I have time, I have a separate deck of slides talking about how HPC is used at other liberal arts colleges and some ideas that I came up with. Challenges. Pomona is not poor. They have a large endowment, but the budget is limited. Not allowed to talk about the numbers. It's just that I did not have millions and millions of dollars to spend on this. Traditionally, HPC environment is very expensive. There's a lack of institutional familiarity with HPC concepts. I saw about 10 hands here reach up when I said HPC. I had 0 people know what that is. I'm still explaining what that is. Software is not really parallelized or version controlled in most cases. And as you probably know, that takes a lot of work. Remote visualization does not exist. Everything is done locally. There are no GPUs. There are data silos. Everything is on local disk. Permissions are all over the place because authentication was not done using central authentication like Active Directory. So UIDs are different everywhere. Nothing is benchmarked or profiled. No idea how long anything is supposed to take. Research and teaching are combined. It's kind of a unique environment. Usually they're separate in academia. There are external collaborators, even international. I don't know if you're familiar with GDPR. How many of you know what that is or what implications there are? About 15 of you. So in Europe, it's going to mean a very complicated data environment where anybody, by the way, not just Europeans, Americans, anybody can go to Europe and go to the GDPR office and say, I want this organization in America to remove all of my data. Systems are not designed for this. This is going to be pretty interesting. It's going to have to go through courts and all that, but if we're responsible citizens, we have to start planning for this. It's going in effect in May. Politics. Other schools are kind of separate. Consortium provides services like phones, and there's a bit of a being careful about how much you say, even around local schools, and I hate that. I like technology, and I hate politics. So Pomona IT is seeding this environment. They're providing the budget, so the priority is on Pomona College, but I'd like to be as open about it as possible to share the experiences with other schools. So one of the first things I had to do was to decide what's a nice to have and what's a must have. I'd like to have as much as possible of the newest and greatest technology. Because it's research, because software varies, not everything runs the same way, and it's a perfect situation in a research environment to test everything and find out how it runs, and possibly even publish a paper, and somebody might benefit from it and not have to waste time doing that again. So sometimes high core count is important, but it's impossible to have high core count and high gigahertz at the same time, so you have to choose. You have to have one of each. GPUs are necessary to augment CPU cores. CPUs are limited in quantity and they're expensive. GPUs are becoming more and more possible to use in a lot of different ways, and they're cheaper and they have more cores, so it's totally logical to include as many of them as possible. NVLinking is connecting multiple GPU cards to make them appear as a single card for higher throughput, for more data processing. Fast shared storage for when you don't want to shuffle data, because the process typically looks like this. A researcher workstation, source data, transfer over 1 gig network to the central environment to a local server disk. It runs, then you transfer the data from that disk somewhere else, so at least 3 times, sometimes more. Fast shared storage among all the systems is ideal. It's possible today. It didn't used to be possible. Central authentication so that UIDs are consistent. A versioning of everything, software, data sets, from the beginning. Configuration control so that the OS and the application settings are consistent throughout the environment because that makes troubleshooting a lot easier. Dockerized everything for portability. Virtualization is too slow, although when there are security concerns, Docker could be inside the virtual machine, but that's a little bit too complicated for the environment that I'm building. So these are the basics. Now, when it comes to hardware choices, there's Intel and AMD. There's basically nothing else. Well, there is, but I'm not considering specialized infrastructures like Superdomes or Cray or PowerPC or Itanium. It's too complex. This environment is too small. Same goes for ARM, FPGAs, and ASICs. There's no time to discuss the differences between these, but if you want to talk to me afterwards, I can explain why I'm not considering those. So it's x86 for software compatibility, and it's choosing between Intel and AMD. Intel is way more expensive, 20 to 30% generally more expensive than AMD. The latest AMD processor has more cores than Intel. So that's a consideration. Plus, I like an underdog. It might have made sense to standardize on Intel, but it's a little bit too expensive, so it makes sense to also look at AMD. So the latest Intel Skylake processor has 28 physical cores per CPU. The latest AMD EPYC has 32 physical cores per CPU. I'm not getting into the detail about the differences between the different brand names of those two, but this is essentially the highest possible physical core count you can have today in a CPU. There's a previous generation of Intel called Broadwell with a maximum of 22 cores. There's no previous AMD generation to speak of. The last server processor they came up with was years ago, so I'm not considering that. The highest you can go is about 3.6 gigahertz, but that's less cores, 6 or 8 or 12, depending. And I settled on the 2-socket systems because 4 or 8-socket systems are not really necessary right now. There is no requirement to have more than 3 terabytes of RAM. Also, they're very expensive. But when you start scaling and you can afford a larger system like that, it makes sense to consider because you can have up to pretty much 64 terabytes of memory with the largest memory chips. So if you want a lot of memory, that's the way to go. Then there was the consideration of how many memory channels. 12, 24, 32 is typical depending on the system. They are split in half between the 2 sockets, 2 CPUs. And then there's the cost of the chips. 32 is the most economical right now. 64 was really interesting, and the prices vary widely. So in some cases, I went with 32. In some cases, I went with 64. 128 is available, but too expensive. 16 doesn't even make sense anymore. So the system's RAM varies between 256 to 512 to 768 gigabytes, depending on those 2 factors. NVIDIA GPUs don't really have a competition. AMD came up with Vega architecture recently, but it's not qualified by vendors yet. If I get my hands on one, I'll definitely test it, but right now, NVIDIA basically has no competition. Intel came up with mics and PHYs a while ago, but they're being discontinued, and there's some interesting things happening at Intel. They may come up with another coprocessor card that will compete with NVIDIA, but right now, it's pretty much the only option. So NVIDIA has desktop cards and server cards. V100 is the latest Tesla brand based on Volta architecture. That's the first time they came up with tensor cores, which are used in deep learning. So it's hardware specific. And then there's previous generation Pascal, that's P100. These are the 2 cards I'm considering for the environment. And then there are other GPU cards like P4 and I forget what the other ones are, but they all specialize. Some specialize in virtualization, some specialize in CAD and GIS, and we may get some of those in, but for right now, keeping it as simple as possible. So desktop GPUs are not considered, although I am using external eGPUs, 1080T, that was the latest and greatest desktop type card until they announced the latest one at the last GTC conference. And basically, USB-C or Thunderbolt makes it possible. It's 2020 for a total of 40 gigs. It wasn't possible before this. So there's a little bit of a difference between Pascal and Volta. It's a more than 10 times improvement in performance or core count, more memory, and like I said, tensor cores. So in a Volta card, there are more than 5,000 CUDA cores and 640 tensor cores. One more consideration. NVIDIA makes its own hardware. They basically have 3, DGX, DGX1, and DGX2. DGX has 4 cards, DGX1 has 8 cards, and DGX2 has 16. Again, that was announced at the latest GTC conference. These are marketed as your personal AI supercomputers. With them, you get access to NVIDIA support, extensive support, starting from the cloud, where a majority of the applications are already Dockerized, so you don't have to spend time doing that, and it's free. And you can download it and run it locally on your infrastructure or in AWS. Digits is very interesting. You have to be a developer. You have to sign up to be a developer with NVIDIA, but they provide a lot of support in terms of machine learning and AI. There is online and in-person training resources, especially in academia. There's access to the user group and pre-installed calibrated NVLink 4, 8, or 16 cards. Microwave is one of the vendors I like. There are others. But NVIDIA basically has to qualify a vendor to resell this hardware. That's important. So Microwave has a Supermicro-based system that also has 4 cards, NVLinked, but that is not supported by NVIDIA. That's important. It's 30–40% less expensive, but not supported by NVIDIA. You're on your own. Microwave sort of supports it, so that's an option. So we considered about 3 vendors, finalized, looked at custom Supermicro versus custom non-Supermicro hardware. Supermicro is generally considered the cheapest, but there are other vendors like Penguin Computing out there that is not Supermicro hardware, and it's slightly better quality, but also more expensive. So you can have NVLink support either way. It just depends whether it's NVIDIA or not. I also was concentrating on getting majority of the equipment from the same vendor. It's easier to simplify purchasing and support. Another consideration that makes a difference in cost is 1 year versus 3-year support consideration. OS is free unless you go with Red Hat. Red Hat, you have to pay for licenses. Cluster management software utility is also from the same vendor, so that makes it simple. The only thing I wasn't able to get from the same vendor is storage, but in the future that might be possible. In terms of cluster provisioning and management, my favorite tool is Bright Computing. There is really no competition out there. HP acquired a French company that does something similar, but not nearly as full-featured. XCAD by IBM is recently discontinued. It used to be a command line tool of choice in this type of environment. I used something called ROX as well. It's out there. There's a website. You can download it, but it's not reliable or scalable. Bright supports all the things you need in an environment like this, like bare metal provisioning, virtualization, Docker. Most of the hardware that's out there that's pretty standard is tested by them. Drivers are available. You would not believe the amount of time that can be wasted when something is not supported by the OS or the provisioning software. And they provide support and even access to code if you need to modify it. OpenStack, Hadoop, Spark stacks, and machine learning, deep learning stacks are included. It's also a significant chunk of time installing and configuring different versions, and they come out very frequently and change frequently. Cloud bursting support for when you don't have enough local resources. Simple NFS-mounted model for software provisioning when the speed is sufficient, or image-based for performance. Essentially, when you have software where it matters that it's local, you can build it into the image, and when the node gets provisioned, it's already on local disk. It doesn't have to go over slow NFS. So some of the things that bare metal provisioning does is PXE boot. So when the physical system boots, it needs an OS. It broadcasts, here's my MAC address, gets the official approved image, boots. You can manage some software in the image. The rest is managed by something like Ansible or Puppet later. It manages DNS and DHCP and NTP, as was mentioned in the first talk. Active Directory LDAP integration. SSSD for caching, that's important. Networks sometimes fail. Sometimes they fail frequently. If your network has a problem, and your credentials are not cached locally, guess what? Nothing will work. So SSD is a great tool that provides caching of credentials locally so that the jobs will continue to run and not crash. But then there's another problem. When you add new users in Active Directory, there needs to be a sync between the locally cached credentials and the newly generated credentials. It also provides metrics and health for real-time and historic data. There's a concept of a head node and a login node in this environment. Head node is essentially responsible for provisioning. You don't want users on that node. Login node is where your users log in, but they don't run jobs on it, because if they run a job that has an out-of-memory situation, then no one can log in. So these concepts are kind of HPC specific. There's also high availability. It's active-passive. There's one node that's constantly being synced to the first one if there is anything changes on the first node, and the failover happens if the first node loses more than one drive. There's reliability on pretty much every level. There's 2 of everything, ideally. So it's very rare that anything breaks. CentOS was the operating system of choice because majority of the software runs on it. The 7.4 is the latest stable. It's compatible with Red Hat, Scientific Linux, and Fedora if somebody needs to run those. Ubuntu is inevitable. And unfortunately, or fortunately, depending on who you talk to, NVIDIA chose Ubuntu for their DGX systems. They come with it, and you support it, and you cannot rebuild it with CentOS. You could, but they wouldn't support it. Also have to support older OSs. There's legacy software, and I'm attempting to Dockerize as much of that as possible to make it more portable. Also planning to support Windows if necessary. There are a lot of users that are Windows only. Post bare metal provisioning is Ansible. I like Ansible because it's easy to pick up compared to Puppet or Chef or SoulStack, and these are the most well-known configuration management tools. Ansible is agentless. I ran into problems scaling Puppet-based environments past, say, 400 nodes. When it grows to that scale, it's better if it's agentless. It's well supported. It was acquired by Red Hat. Typically, Ansible is command line, so if you need to know exactly what was run and when and by who, you have visualization tools like Ansible Tower, which is the commercial version, and Rundeck, which is open source free version. It's essentially a workflow visualization tool. If your data moved, if you changed software in any way, you can have a timestamp of when it happened. Everything is versioned as much as possible. Git or GitHub for everything. It's hosted right now. We don't have the resources to host it locally. The current structure is applications, design, discovery, systems, and training. Those were logically separated. The idea is to basically use it as a glorified wiki for now, and when the system is built, the information about how the system was designed is already connected to the scripts that configure the system, so that you don't have to go to another place to look it up. So system-specific files exist along with documentation right away. The scheduler that is used is Slurm. I've used a number of others. This one is basically free to use with commercial support if you need it. It's very scalable. It has a lot of concepts that make sense, and it pioneered a lot of concepts. You typically want to have accounting. That's important, especially in academic environment, because chargeback and grants are everyday things. Every single piece of equipment typically comes funded by a grant, and people like to know that it's their hardware and they are using it, and maybe other people have access to it when it's not used, but they get the priority. So accounting, meaning who runs the jobs, how big the jobs are, how many resources they're using, how long they run, all of that needs to be recorded and analyzed. XDMod is a really good visualization tool that was developed at Exceed, which is a grid system among multiple educational institutions. Fair share is a concept where you have people with large jobs that may not have enough nodes. So they will be sitting there and hogging the nodes that are not used. So if there is a short job that could complete under an hour, it could jump in and complete while the larger job is waiting for resources. Also, counting who submitted how many jobs and making sure that they're not hogging the resources. There are queues, and they're differentiated between short jobs and long jobs, single core, multi-core, production development, interactive, and RAM intensive. Those are typically very different jobs. Interactive is important in this case. Not everybody has a script with arguments and input and output. They may want to play with the system to figure out the optimal core count or the optimal configuration. And then some jobs will take all the memory on the system. So you do want to reserve a node for that job because you don't want to share the memory with other jobs. There is also typically pre- and post-job script that may involve moving data to or from the system. But typically, this is SSH batch script with arguments, input and output, very simple, not changing. Time limit is very important. If it's not set, then you cannot enforce fair share, and you cannot kill jobs that are stale or stuck. So scheduler is a very typical thing for HPC, and it's very different from Kubernetes scheduling or swarm scheduling. This typically has to do with people submitting actual jobs with batch scripts and data. Networking. Mellanox Ethernet is the most things that makes most sense cost-wise. It's an Ascent 2700B, which is a relatively large port count, 32 ports. It's not cheap, but it's cheaper than InfiniBand. This supports 1040 gig, which is becoming more and more common. Most data centers today are 10 gig at least. 100 gig is available today. It's coming down in price, but it's still 30 to 50% more expensive. InfiniBand in this case is overkill. InfiniBand, how many of you know what InfiniBand is or used it? Wow, okay, 4 people. So it's a specialized networking when latency is important. Just to give you an idea, InfiniBand is 60 to 90, depending on the equipment. Ethernet is 300 and up, somewhere around there. So 5 times or so difference in latency. So when you want an operation to complete faster, you want shorter latency, you want InfiniBand, but it's 30 to 50% more expensive than Ethernet, more difficult to configure, more difficult to support, more complicated, needs more tools. When you're using message passing interface, OpenMPI or MPitch or anything else, InfiniBand is probably something you should be using in your environment. Why would you use message passing interface? When a single physical system is not enough to process your data. When you want to scale across multiple systems, you want to use MPI. It requires programming, it requires custom code. In terms of networking, compute and storage typically need to be separated because they both are very intense in I/O, and they could cripple each other, and that's not good. So the budget did not allow for 4 switches. Typically, I would do redundant compute and redundant storage, but in this case, it's okay to have VLANs. So they're split in 2. Both switches have storage and compute, and if one switch fails, then everything continues working. QSFP plus for connectivity, dual port cards and nodes, 1 for compute, 1 for storage. Pure storage is what I chose for shared storage. It's very expensive, but it's the best and the fastest you can get out there right now. At the bottom of the slide is their lineup, with an M10 being the smallest. All flash NVMe is available, I believe, only in M70 and X70, but that's the fastest possible storage out there if you want to have shared NFS mounted, or iSCSI, like in the case of M10. There are existing Windows home directories that I'm going to use for now. Not ideal, but I don't want to disrupt the environment too much. Centralized authentication with Active Directory. The choices of drives are 512 gig, 1 or 2 terabytes. In M10, there are 20 slots. And in some cases, we are going to use local scratch because networked storage is slower than local disk. And with Intel Optane promising speeds in I/O close to memory, it makes sense to use it for scratch. It's about 300 gigs, 384 gigs per disk. And in the future, we'll be building a parallel file system. I don't have time to get into the details of the difference between parallel file system versus, say, NFS. POSIX is the most important one there. And object storage for cold deep, basically cheap storage to offload from your expensive fast storage. And some version of data lake so that the data doesn't have to constantly move in and out the environment. The idea is for the data to ingest, stay there, people work on it, store the results there, send it somewhere else if necessary, but for I/O, it's best if it doesn't leave the environment. Monitoring. Bright has built-in real-time and historical monitoring. Slurm plus XDMod is for visualization of how long the jobs run, how many, what type, and who is hogging the queue. Hosted elk for logs and anomaly detection. They now have also machine learning, so it's considerably improved since version 1 that came out in 2013, I think. CheckMK for pulse and alarms. Are things up and down? Are things red or green? Nessus Pro and Tenable for vulnerability and patching. I don't know how much you're aware of the hardware patching that's required these days. It's becoming the norm and a regular thing. And I like Riemann for correlation. So that's for highly custom situations for when you want to detect a certain thing that's recurring, connect it to some other things that's possibly recurring, and then make a decision what to do about it and execute an action. Support. It's just me for now. I have an applications manager who knows everyone, and we talk to a lot of people, attend a lot of faculty meetings. For the summer, I might have 1 to 2 students. And there are plans to grow the team as the environment stabilizes with the focus on software support, because once the hardware is provisioned, you hardly ever touch it. In terms of software, this is just some of the examples of the software used, potentially hundreds of software packages, commercial, open source, you name it. We cannot restrict the research, so we'll support everything. Kubernetes for scaling established workflows. It now supports GPUs. Docker supports GPUs, so we're definitely planning to use them. There are some links there for more information. With containers, there's the issue of persisting the storage. So I like Minio. Weka.io is a great company, but it's commercial only. I don't think there's a free version. But either one is good for persisting storage in the container instead of having to remember to move your data from the container when it's processed and ready to go somewhere else. Because if your container is shut down, you lose that data. Exploring virtual reality, augmented reality to integrate with this environment, building a lab, and potential blockchain use for things like credentials and more. And I don't know if questions are allowed here, but if there's time and or interest, we could do questions. I don't think there's time for the other slide deck, but I'll make it available at the end of the conference so you can take a look at the use cases at liberal arts colleges and how they would use this environment. So, do I have time to show the second slide deck? I guess unless I get yelled at, I will do it.
Okay, he's in.
No?
See or no?
Okay. I guess we're done then. Since everyone's still here, I'll quickly run through this. So the first mentions of HPC in liberal arts was as early as 2005 at Oberlin, and then reoccurred again in 2014, mostly in conjunction with computer science department. The Illinois College of Liberal Arts and Sciences in 2017 made some waves with supercomputing, studying Earth's interior. Teagle Foundation on the East Coast is producing some reports about a 6-college consortium in Upper New York. Harvey Mudd, which is one of the schools in Claremont, made some waves with GPUs and custom-built GPU systems. Emory has high-performance computing as a concept. Reed College has, again, mathematics and CS driving this. Bowdoin College got involved in 2015 at the supercomputing conference. Stanford, you probably know Stanford pretty well. And then Pomona Use Cases in physics, like fluid dynamics, flow simulation, ANSYS, and OpenFOAM, star CCM. In chemistry, molecular modeling. In biology, BLAST, and a lot of other tools. Linguistics, it's proprietary software that mostly does natural language processing. There's a lot of interesting work that was done at Baidu's AI lab about this. In astronomy, the use of Mathematica and a lot of statistics. In psychology, brain imaging and simulation. And concepts like Semantic Web and Web 3.0, where all the data is available and you can model it, easily access it and share it. And there's a conference on liberal arts and AI and what it means. You probably know there are a lot of ethical issues with using AI responsibly. So I feel like it's a liberal arts issue. Ontology design patterns is another interesting path. And finally, visualization software, remote visualization is important. If you go to Exceed, there are hundreds of software packages. We will not be supporting all of these, but a large portion of these. And finally, San Diego Supercomputing Center is another well-known resource for the software running on HPC. Science Gateways is a concept that simplifies access to this environment via a web interface and makes data discoverable, and basically helps researchers make sense of this. It's a highly complicated environment. Done. Thank you.